For thousands of years, man has believed that he was the beginning and end of creation. But this certainty began to be shaken a little over a century ago, when Darwin exposed man as a product of the evolution of the species. In the 21st century, science has broadened man's horizons and places him within the evolution of the universe. Man now appears as part of the cosmos, as a diminutive being who, thanks to an incredible miracle of chance, is able to look into the infinite in order to write the history of the universe. This image of a television before picking up a station is an echo of the Big Bang. Some of these points on the screen are produced by the radiation that the great creative explosion generated. They are photons that are still reaching Earth from the period when the universe was in the first phases of its expansion. Other particles from the infancy of the cosmos also reach our planet and are much more difficult to perceive. They are the neutrinos that go through our bodies constantly. They are one of the components of dark matter, a force that has taken the lead in a new anatomy of the universe that man is beginning to dissect. Most scientists believe that the physical world emerged around 14 billion years ago, from a microscopic point in which an almost infinite amount of energy was concentrated. Its density was so great that it ended up exploding as if it were a great nuclear oven. The energy liberated in the explosion then began to expand in all directions, creating a new reality. We do not know what existed before, but after the Big Bang, our space appeared and time began. And with space and time, everything that they contain: galaxies, planets, stars, even human beings.
I think there was a long time when people thought, well, we could think of other theories, besides the Big Bang theory to explain where the universe came from. And we had Fred Hoyle and his colleagues trying to come up with a steady state theory. The idea the universe is expanding, but as space expands, new matter appears, and you can get that new matter coalesces to form new stars and so forth. And in that universe, it's very psychologically appealing. It's a universe where, the universe always was and always will be, and it's always being refreshed. But the Big Bang is very different. It's this moment of creation, or this big element of creation, that suddenly, poof, you create a huge amount of time, of space and time, and the universe starts evolving furiously and spectacularly, and you get more space and more time, and all these particles and things in the universe, and they're all sort of, looks like they're going through chaotic motion and everything. And as the dust settles, they sort of gather together, and you first end up making protons and neutrons and electrons out of it, and then you form the atoms, and then the atoms form the various things. You get this, this evolution going on, but it tells you there was a beginning, and there will probably be an end, and it may be it may be a catastrophic end where things crunch together, or it may be a sort of a whimper end where everything gets diluted down to where it's just garbage everywhere.
To reach this contemporary view of the creation of the universe, with its beginning and end, many beliefs and forms of thought have undergone complete revolutions. Classical culture believed that the universe was stable, that it did not change. Newton was also convinced of this, and even Einstein too, before we discovered that galaxies travel, moving away from the center of the big explosion. Thanks to this new paradigm, Our cosmic destiny depends on such concepts as radiation, space-time, or the void. It does not provide answers as to why we are here, but it is upheld by a scientific certainty, the model of the Big Bang. The model of the Big Bang, or the theory of origin, began to be hatched in the 1920s when the U.S. astronomer Edwin Hubble studied the galaxies. From his telescope on Mount Wilson, he perceived that they moved away from each other as if the entire universe were expanding. The movement also indicated that the matter had been closer before. And if one turned back the hand of time into the past, one could reach a moment when it was all compressed or compact. These observations on the galaxies led the Russian-American astrophysicist George Gamow to formulate the first statement of the Big Bang Theory, or the Great Explosion, that created the universe as we know it. To demonstrate the validity of such a surprising theory, scientists first had to find the traces of the explosion. And given the magnitude the cataclysm must have had, Gamow deduced that one would have to be able to detect the radiation unleashed in the blast throughout the entire universe. Because due to the law of conservation of energy, the radiation would not have disappeared. In the early 1960s, the astrophysicist Jim Pebbles of the Institute for Advanced Studies in Princeton started to look for this radiation. But two other physicists, Arno Penzias and Robert Wilson, found it when trying to eliminate a bothersome noise captured by antenna. It was background radiation, the first proof validating the Big Bang Theory. Shortly thereafter, the theory received new backing with the verification that the universe was mainly made up of two basic elements, hydrogen and helium, and in the exact proportion predicted in the theory. Both discoveries provide physics with its creation myth, since now everything indicated that there was a common origin for all matter. After establishing how the universe must have originated, cosmologists had, and still have before them, an even greater challenge: to write its history, to know what happened from that instant on.
So I have 99% confidence that there was a Big Bang. Not 100%, because of course we could be wrong. We could be as misguided as a Ptolemaic astronomer who's discovered another epicycle, but 99% confidence. But let me add one more proviso. That 99% confidence applies to the Big Bang Theory back to the stage when the universe was about 1 second old, nearly to the beginning. But if you want to ask what happened within that first second, in the first millisecond or the first microsecond, then we are far less confident. The reason for that is that when we go back to the first tiny fraction of a second, the universe was so hot and so dense that the conditions were beyond anything we can simulate here on Earth or test experimentally in the laboratory. So when we get to the first tiny fraction of a second, we lose our foothold in experiment and things become uncertain.
What happened immediately after the Great Explosion is one of the most difficult enigmas current cosmology has to figure out. Scientists are faced with a theoretical problem that has no easy solution. The fundamental law of the universe, the law of gravity that determines attraction among matter, was not functioning during those first moments. If it had, the matter that originated after the explosion would have contracted again, since its great density would exercise a strong attraction to itself.
We have a very good theory which explains the behavior of atoms. This is what's called the quantum theory. We also have a good theory of gravity, which Einstein developed, called general relativity. But we don't have a theory which combines gravity with the quantum principle. This normally doesn't matter because in most parts of the universe we don't have to worry about gravity and quantum theory simultaneously. Gravity is important in big objects like planets and stars, whereas quantum theory is important only in single atoms, where gravity is unimportant. But if you imagine the very beginning of the universe, when something as heavy as a star is squeezed down smaller than a single atom, then you have to worry about gravity and also about quantum effects. And we have no theory that combines those two phenomena.
To explain this anomalous behavior of matter, which, defying the laws of gravitational attraction, expanded instead of contracting, the physicist Alan Guth has proposed a theory of inflation. It's not fully accepted in the scientific community, but it is a most suggestive idea to explain why this colossal expansion was produced.
Inflation is really an attempt to answer the question of what was the bang of the Big Bang? What is it that set the universe into expansion? And the answer that the inflationary theory proposes is that the expansion was started by a peculiar form of matter which can turn gravity on its head and cause gravity to become repulsive. In fact, today we've recently discovered that the universe appears to be accelerating, which means that perhaps there's a density of a similar type of matter filling the universe at the present time. But what I'm talking about is something which would have been much more dramatic, a material with a much higher density of matter, much higher energy density that would have existed in the early universe, which could have caused the universe to start to dramatically expand at a fantastic rate.
In the smallest fraction of the first second of time following the Big Bang, the forms and kinds of matter that compose the universe were determined. Then, at that moment, in accordance with some strange physical laws, it was determined that matter would be grouped and distributed in a very peculiar way, forming galaxies or accumulations of stars. We find ourselves, therefore, facing a new and strange cosmic code. The universe's behavior seems to be governed by new and strange laws. Dark matter, gamma rays, and black holes are realities and basic elements of the universe's structure that were detected when man, thanks to the technological development of telescopes, became aware of the limitation of his vision. The human eye sees only a small part of what electromagnetic radiation produces, that of the light that is visible to us. But the greater part of the universe's reality is evidenced in other wavelengths that we cannot see, such as infrared and ultraviolet radiation, radio waves, X-rays, or gamma rays. This new and disconcerting face of the universe is the greatest challenge of human knowledge. And thanks to astronautics, inscrutable outer space has come even closer to man. It all began in 1957, when the former Soviet Union put the first artificial satellite, Sputnik 1, in orbit around the Earth. Thus began the space age, whose first human traveler was the Russian Yuri Gagarin in 1961. Since then, nearly 50 people have left the atmosphere, and 2 of them, the Americans Armstrong and Aldrin, became great figures of the 20th century when they took the first human steps on the moon. Another Russian, Maranov, boasts the record for remaining in space after staying a little over 1 year on the Mir space station. With astronautics, the universe ceases to be an object of observation and becomes a place to be conquered and colonized. Thus, the most audacious hope is imagining a future in which permanent human communities can be established on large space stations, once the conditions of limited gravity in nearby outer space are controlled. Telescopes draw a more complete and real map of the universe for us, while satellites and space probes allow a direct experience of the cosmos. Given the immensity and creativity offered by this new image of the universe, it's inevitable to wonder whether or not human beings are the only conscious inhabitants of such an immense expanse. With the exploration of space, the desire to seek other forms of life seems inevitable. To seek evidence of settings similar to our own planet, which might help us figure out the enigma that emerged from the Great Explosion that still continues expanding time and space. This image shows the universe when it was a mere 300,000 years old. It was taken in 1992 by the Kobe satellite, sent up by NASA to study background radiation, and it served to prove that there were some areas with greater density of matter than others, as if, after the Big Bang, matter had not been distributed homogeneously in all directions throughout space. Once again, the universe disconcerted cosmologists upon showing that matter had accumulated in areas of space where later the galaxies and their stars had formed. The rest was empty.
El universo empezó siendo muy pequeño, muy caliente.
When the universe began, it was very small, very hot, and very homogeneous. That is to say, matter was distributed in such a manner that there was the same density everywhere, the same quantity of matter, but only approximately the same. In some regions, there was a little bit more than in others. And with a process that is called gravitational instability, what happens is that when you have an area in which you have a little bit more matter, that area attracts still more matter from the regions around it. And the more matter you attract, the stronger the gravity of the region, so that it attracts even more matter. That is to say, it's a process that refuels itself, so that more matter attracts more matter, and so on. It just keeps growing. So that what began by being some microscopic fluctuations in the universe's matter has grown during the entire life of the universe until today. And as these small fluctuations grew, they joined with other regions which also grew in the same way. And they ended up forming the quantities or the agglomerations of matter that today make up the galaxies.
Nothing is static in the universe. Everything always turns around something. If the planets revolve around a star, the stars, grouped among themselves, revolve around a center of the galaxy where a great number of stars accumulates. But on many occasions, cosmologists have observed that the density of the matter that is seen in the galaxies is not sufficient to keep the stars together gravitationally by themselves alone. This has led scientists to deduce that there is a force of gravity of an unknown origin that seems to be determining the movement of the stars. This mysterious force is known as dark matter, a kind of energy mass that is not visible or detectable, at least for human beings, and that surprisingly could constitute 95% of the universe. What might a matter of which there is no physical evidence and whose existence is known only through logical deduction be made out of?
The atoms that we and the Earth and the stars are made of are actually less than 5% of all the stuff in the universe. The other 95% is in some more exotic form. Quite a lot of it is in so-called dark matter, particles probably left over from the Big Bang, which don't shine and don't interact with anything else, but exert a gravitational pull. So we have three kinds of energy and matter in the universe. We have the ordinary atoms, we have dark matter, and we have dark energy in empty space.
Discovering the composition of this dark matter is one of the central problems of cosmology. Scientists are trying to determine the density of the particles that form it, since the role of its gravitational force in the future evolution of the universe depends on it. A future which scientists say may entail the collapse of all matter, or its perpetual expansion.
Dark matter is also very important because it determines the fate of the universe. Everything in the universe exerts a gravitational pull on everything else, and if there was sufficient dark matter, then the cosmic expansion would eventually halt and the universe would recollapse to a big crunch where everything would be destroyed. It's now clear that there is not enough dark matter to halt the expansion of the universe, and that the universe will go on expanding forever, probably even at an accelerating rate. So the long-term forecast for the universe is that it'll become ever emptier, ever colder, but it'll go on expanding forever. The stars will all die out and become more dilute, but the expansion will continue forever.
In January of 1999, the biggest cosmic explosion detected to date by human telescopes took place. At 7 billion light-years, a hypernova was observed, a hyper-explosion whose magnitude has been established in terms of the brilliance observed from Earth. If that brilliance is more or less similar to that of the galaxy where it is produced, it's a supernova or exploding star. But if it's much greater, it's called a hypernova. It's not known whether the glow in 1999 was due to two galaxies interacting, or whether it was a process of intense star formation, but it's hard to imagine the energy it liberated, equivalent to some 30,000 quintillion atomic bombs like the one that fell on Hiroshima. By capturing these phenomena, modern astronomy offers a very different image of the sky from that ideal view of a peaceful heaven illuminated by lights that reflect the constancy of eternity. But the universe is not infinite, nor is it timeless as was traditionally thought, but rather it had a beginning and it could have an end one day. Its history is, above all, a record of violent episodes, since only through the conflict and collapse of cosmic matter has the interstellar medium been able to form. When a very massive star collapses on itself and explodes in the form of a supernova, or when cosmic explosions of gamma rays take place, they are moments of creation in the cosmos, moments in which the universe is regenerated with the elements that make way for the birth of new matter. Cosmic violence can reach unfathomable limits, however, such as when everything, matter, energy, and light, disappears, swallowed up by the most disconcerting phenomenon of galactic anatomy yet, black holes. The concept of the black hole was already anticipated at the end of the 18th century by the astronomer Laplace, who posited the possible existence of an object so dense as not to let anything escape from it, not even light. From there the name black hole. The theoretical mathematical formulation of the black hole was generated in the 20th century and states that when a star of enormous volume exhausts its fuel and dies, the force of gravity inside of it pulls towards itself, thereby provoking a total collapse and becoming a black hole. It's a region of space with a gravitational force so strong that it provokes a strong curve in space-time. For physicists, a black hole is the greatest singularity of space. That's to say, one of those phenomena in which the laws of physics do not have effect. The matter trapped by the gravity of a black hole begins to revolve around it, forming a flat structure of gas called the accretion disk. The quantity of matter that falls is so great that it doesn't have time to cross the surface of the black hole and disappear. It accumulates in the surroundings, waiting in line to be devoured. This is the border region that marks the limit from which nothing can escape that infinite unknown. It's called the event horizon, and it's the zone in which, if we could detect how matter falls towards the center of a black hole, we would see its image frozen just before it disappears, since we could no longer follow its trace when not even the light that illuminates it escapes being trapped. That is where we lose track of the light, the cosmic messenger that, thanks to telescopes, allows us to observe the universe. In 1609, when Galileo pointed to space with his first simple telescope with 3 magnifications, he revolutionized astronomy. With his rudimentary apparatus, he discovered that Jupiter had satellites, that the moon's surface was rough, that Saturn was wrapped in a halo, and that the Milky Way was made up of millions of stars. Without telescopes, modern cosmology could not exist. Everything that is known today about the cosmos has been deduced from the light signals that telescopes capture and analyze, signals that since the Big Bang have been running through time and space, leaving in their trail the trace of everything that has occurred in the history of the universe.
A telescope is basically a collector of photons. If we simplify it a lot, it is like a funnel. What we do is concentrate the very diluted energy that comes to us from the outer world into the focal point, and we do everything we can to be able to extract this information. The larger the collector's surface, the farther we can reach, and the greater the quantity of energy we can collect, which comes to us quite diluted. The truth is that telescopes are the only time machines. When we say that we are looking at a star that is at a distance of hundreds or thousands of light years, we're saying that it is at an enormous distance, because you have to multiply each second by 300,000 kilometers, which is the speed of light. Furthermore, we are saying that that light left the object hundreds or thousands of years ago, and when we speak of galaxies, we're talking about billions of years ago. So when we penetrate distances with a telescope, we're going back in time, and large telescopes attempt to reach, if possible, the origins of our universe.
Llegando a ser posible a los orígenes de nuestro propio universo.
Astronomers also study the universe from observatories situated outside the Earth, thanks to space telescopes, which allow us to see space without the veil of the Earth's atmosphere. The Hubble is the oldest of these devices. Put into orbit in 1990, it weighs 12,000 kilos, is 9 meters long, and has a 2.5-meter diameter mirror. From its lookout point at 600 kilometers from the Earth, it has taken thousands of digital photographs of the universe that astronomers later transform into images. This one, for example, shows a star with a mass similar to the Sun's, but which is already dead and has hardly any energy left inside. In its process of decomposition, 1 million years ago it began to expel gas in opposite directions. It's known as the Calabash Nebula and is located 5,000 light-years from Earth. Thanks to the Hubble and other similar telescopes, other forms of invisible light or radiation that do not cross the Earth's atmosphere, such as ultraviolet and infrared radiation, X-rays, or gamma rays, can be captured. Gamma rays are precisely the most intense radiation of the universe, and they are behind the most violent phenomena and objects, such as black holes, neutron stars, or the active nuclei of the galaxies. When the universe had already spent 10 billion years expanding and recreating itself, in a corner of the Milky Way, a simple cosmic garden began to be formed, which with time would come to accommodate life, our solar system. A cloud of cosmic dust crossed with the remains of a great star that had just exploded. The matter that emerged from the crash collapsed on itself. This collapse turned the gravitational energy into kinetic energy, and the temperature rose so much that it provoked thermonuclear reactions. A proto-sun had been born, around which the rest of the nebula began to revolve like a disk. Little by little, all the materials of the nebula were cooling down, and the cosmic dust was turning into great mineral chunks that would help form planets. Once the proto-sun became the sun, an enormous source of heat and radiation was originated that swept the system of all the material that hadn't condensed. That was when those great blocks of matter that revolved around the new sun were colliding and forming groups among themselves until they reached the form and size of the planets. The solar system thus remained constituted by a star surrounded by planets and other cosmic elements like asteroids and comets that revolve in almost circular orbits. It's this system which permitted the appearance of life on Earth, thanks to the violent protection of the Sun.
La edad del Sol, su origen, cómo se formó.
The age of the Sun, its origin, how it was formed and what its future evolution may be, constituted one of the main concerns of science during the first third of the 20th century.
Hoy en día tenemos las cosas relativamente.
Nowadays, we are confident on several points. We know that the Sun produces its energy by means of the transformation of hydrogen, the principal component of the universe, into helium. In this process, it loses a little of the mass that is transformed into energy. Today, we estimate that there's enough fuel for the Sun to keep shining in this way, more or less stably, for another 4 to 4.6 billion years.
4.600 millones de años.
The space probe Ulysses and the SOHO explore the surface of the star of the solar system. The images show a very imperfect star, full of turbulences and protuberances, with great masses of matter forming magnetic whirlwinds on the surface. They are sunspots that reflect the different densities and temperatures of these magnetic whirlwinds. Every so often, they provoke sunstorms, perturbations in the surface from which millions of ionized particles shoot out to the exterior. These particles affect the Earth's magnetic field and cause such spectacles as the Northern Lights. The exploration of our nearby cosmic environment, the solar system, has not been completed yet. While it seems clear that there are no signs of intelligent life on the neighboring planets, scientists are looking for evidence to prove that other forms of life are possible. In the first place, the conditions necessary for living beings to reproduce themselves, even if in the most simple forms of bacteria, must be determined. They don't have to be exactly the same as those on Earth, but they do seem to require the existence of certain elements, such as water, an organic matter like coal, and a source of energy that makes the chemical molecules that might exist react among themselves. Europa is one of Jupiter's satellites, in which in the long run, scientists have placed the most hopes of finding traces of life. There are reasons to believe that water has existed there for some time, and that under its frozen surface, there is an enormous ocean full of organic molecules. In the orbit of Saturn, the other gaseous giant besides Jupiter, the satellite Titan presents certain similarities to Earth, which also need to be studied. According to the images that the Voyager 1 space probe offered, Titan is surrounded by an orangish atmosphere composed above all of methane. This element appears to be found in solid, liquid, and gaseous states, so that it could act as water does on Earth, as a life-giving element, with cells which carry it inside them, just as ours carry water. While Europa and Titan await their moment, biologists and physicists continue to study the best and closest candidate to accommodate or to have accommodated life, the planet Mars, where few doubt that at least there is water. In 1975, the exploration of Mars began with NASA's Viking space probe, whose journeys over the land's cold, barren, and irregular surface provided no positive results. Almost 30 years after the Viking mission, a new space probe, the Mars Express, follows the path of many other probes sent to Mars. This time, the project is sponsored by the European Space Agency, and it's a satellite that will place itself in the planet's orbit, from where a landing module will be released. Thus, Mars will be photographed both from its sky and from its surface, and its physics and chemistry will be analyzed inch by inch over a broad expanse. The vehicle that will land on the planet will even be able to take samples of its subsoil to a depth of 1.5 meters. One of the factors that has most stimulated the search for life on Mars once again is the study of meteorites found on Earth which came from the Red Planet. In particular, the ALH 84001, found in Antarctica in 1984. It's still being studied today, along with others like it, because scientists cannot agree on what it represents. Its defenders, however, are certain that it is a meteorite from Mars with fossil traces of certain living beings. This exploration of the solar system offers us the opportunity to investigate cosmic archaeology. We find fossils or cosmic remains that come from remote times in which the comets and asteroids were formed 5 billion years ago. The comets are more interesting. They are accumulations of ice and dust condemned to wandering through the solar system eternally, tracing very eccentric orbits. In the mid-1980s, the European Space Agency launched a probe to meet Halley's Comet, which appears in our sky every 76 years. The probe's name, Giotto, refers to the Italian master in whose painting The Annunciation the comet appears. The space probe provided very valuable information. Amino acids were found in the tail of Halley's Comet. These chemical elements are the base of proteins. Therefore, part of the raw material from which life is generated exists outside the Earth. Since the Giotto, the European Space Agency has concentrated on the Rosetta probe. It will be directed to the Wirtanen Comet, which it will meet in the year 2011, and for the first time, it will install itself in the nucleus and not in the tail. There it will remain for some time to accompany it in its trajectory, traveling at 135,000 kilometers per hour and experiencing with the comet all the changes in its temperature as it gets closer to the Sun. Like the stone from which it got its name, the Rosetta Stone that helped Champollion decipher the Egyptian hieroglyphics, this probe will reveal the interior of a comet. It will draw maps, take photographs, and will analyze the particles of dust and gas in its tail, a trace that is formed when its ices evaporate because of its proximity to the Sun. We have to accept that the Earth is the only point in the solar system that at present accommodates intelligent life. But the universe is so large that simply according to statistical probability, it's safe to say that there are hundreds of similar planets. In just the Milky Way, our galaxy, it is calculated that there are some 100 billion stars, of which many could resemble the Sun. Are these stars, like our own, the core of a planetary system that may be fertile?
Since 1995, we have discovered the existence of planetary systems in which there are planets that revolve around other stars that are not the solar system. This increases extraordinarily the possibilities that life may exist in other places in the universe. And furthermore, it reaffirms something very basic, and that is that the very emergence of the solar system is also a consequence of the universe's evolution. If, in the emergence of the solar system, life appeared on the planet Earth, and if other planetary systems exist in other places in the universe, and if conditions arise similar to those that appeared in the solar system some 4 billion years ago, then life could also appear in those places in the universe.
4.000 millones de años, pues también podrá darse vida en estos lugares del universo.
The search for planets outside the solar system is one of the areas of greatest development in astrophysics. This research comes up against a major obstacle, since the planets, as they do not emit light, are not directly detectable. Only stars can be seen from the Earth with the telescopes currently available. Cosmologists observe the movement of a star to figure out whether planets exist circling in orbit around it. If a star is the center of a planetary system, it also moves, tracing a small orbit around its central position. This movement would not occur if it did not have planets around it. With a technique called the Doppler technique, which analyzes the infrared spectrum of the light the star emits, it's possible to verify whether the star moves or not. When the star moves toward the point from which it is being observed, the spectrum acquires a blue tone. If it moves away, it changes to red. Thus, if the spectral lines of a star show this movement of coming and going, it surely has a planet revolving around it. More than 100 stars have been detected with planets of many different kinds. There are those that are more or less similar to Jupiter, and others as small as Earth. In some cases, they have even been shown to have an atmosphere, which augurs well, since atmospheres tend to regulate the usually extreme temperatures of many planets. Discovering planets similar to the Earth and finding life in them would achieve full meaning if the beings found there had an intelligence that allowed for communication. But scientists have been very cautious in public and speak above all of the possibility of life in its simplest forms. For them, it would be almost a miracle if any trace of life could follow an evolution as difficult or unpredictable as that which, through its tortuous path, has permitted man's appearance on Earth. But it is human nature to create other more visionary scenes of the future. From communicating with highly advanced beings with extraordinary skills, to deciding to take on the real conquest of space. Perhaps for that moment to arrive, man himself must make an evolutionary leap that would allow him to travel at the speed of light. Science fiction, always ahead of its time, has already dreamed of such things, although scientific theory has also formulated it when describing a motor that feeds on antimatter. Thus, in accord with Einstein's equation, antimatter could be created, making it collide with matter and obtaining pure energy. With that, those distant planets could be reached in a few years. The Big Bang Theory explains the origin of the universe. It's also known that the 14 billion years that have already passed are no more than the beginning of its history, since, given the force of the energies that govern it, it is impossible to put a date on its final destiny. It's not even known with any certainty how it will end. If existing matter were not enough to overcome by gravity the force of its expansion, the universe would become an almost infinite space, practically empty and completely frozen. But if, on the contrary, gravity is capable of stopping the expansion and initiating a contraction of everything the universe contains, then a Big Bang in reverse would be produced, which scientists call the Big Crunch. All the stars would approach one another at increasing speeds until they collided, and then they'd start condensing. In the end, the entire universe would once again be contained in a single point of density and with a nearly infinite temperature. From this perspective, the history of mankind is no more than an insignificant anecdote in the immensity of the universe. It may be, however, that there are very few beings like ourselves that have such a great tendency to ask why the cosmos exists and for what purpose.